In relativity, we're going to talk a lot about events and the coordinates of the events. And what we're going to see is that the coordinates of events depend on reference frame. In other words, the x, y, and z and time coordinates we assign to events can depend on your reference frame. But there are some quantities that do not change and are constant across all reference frames. In preparation for getting our mind in that place, I want to make an analogy to just geometric arguments. So what we're going to do is bring in a picture here that shows 2 points on a plane. We have an XY plane, so you can think of this as like the floor, the ground. And the red dot here represents where you live, say your home, and the blue dot represents where you work. And let's say this is a coordinate system labeled XY, but let's be even more specific. Let's call it XA for Alice's reference frame and YA. So Alice in her mind is kind of setting up a grid on the ground, and she's assigning points on that grid. And her grid kind of runs east-west, let's say, and north-south. So X for her is east-west, and Y is north-south. And on that grid, she identifies the coordinates of this point, this blue point, and she would label them, Alice would label those coordinates as 4, 3 for an X coordinate of 4 and a Y coordinate of 3. So we actually can write this down. Let's say we'll say Alice, and then later we're going to introduce Bob. So I'm going to create a table here with Alice and Bob, and we're going to write down the coordinates that Alice assigns for each of these points. So Alice would say her home is at the origin, 0, 0, X, Y, and her work is at 4, 3, and these are units of kilometers, just to pick a specific case. Okay, so Alice has chosen to use east, west, and north, south as her coordinate system. But along comes Bob, who's a little bit contrarian, and he decides east, west, north, south is too straightforward. He wants to have a different coordinate system. So Bob chooses a different coordinate system. We're going to indicate that with a green line. And he actually chooses a coordinate system such that his x-axis goes right through the 2 points of interest. So we'll label this xb for Bob's x-axis, which is in kilometers. And we will label, we want another axis here. It's going to be perpendicular to the first, and that will be his y-coordinate system, or his y-coordinate, again in kilometers. So we'll label that y sub b for Bob's y-coordinate. And Bob then would disagree on the coordinates of these points, right? First of all, we can write down the coordinates for these 2 points, home and work. And for Bob, notice the red dot is still at his origin. So actually he will agree with Alice that home is at 0, 0. Work, however, he will disagree. He will say, no, it's not 4, 3, because the blue point is on his x-axis. And a point that's on his x-axis has a y-coordinate of 0. So Bob says the y-coordinate of his work is 0. Well, what is then the x-coordinate? Well, we have to do a little math to figure that out. But recall from geometry and Pythagorean theorem that you can have a triangle, and if the lengths of the 2 sides of that triangle are 3 and 4, then the hypotenuse will have a length of 5, a 3, 4, 5 triangle. And if you like, you can remember that the hypotenuse length is equal to the square root of the sum of the squares of the other 2 sides, in this case 3 and 4. So we'll have a square root of 9 plus 16, or the square root of 25, which is 5. So a 3, 4, 5 triangle means that the distance along one edge is 4, the other edge is 3, and this hypotenuse, which is the x-coordinate in Bob's frame of his work, will be labeled 5, because it's 5 units away from the origin. Okay, so he's now going to put this 5 in here for his coordinate. So Alice and Bob agree that home is at 0, 0, but they disagree on the label for work, right? Because the office for Alice is at 4, 3, but for Bob, it's at 5, 0. So you might think, okay, so this is an example where if you rotate a coordinate system, you change the labels of the points as described in those coordinate systems, okay? With the exception of the point that's at the location of the rotation, because that point hasn't moved relative to the reference frame, but the blue point has. So a perfectly reasonable question then is, well, is there anything that doesn't change? Is there anything that's conserved or constant? And I think your intuition will suggest yes, right? Like the distance that you have to drive from your home to your work should not depend at all on the coordinate system that you choose, right? Whether Alice or Bob describes the journey, they have to both agree that it's 5 miles or 5 kilometers of a drive from home to work, right? Whether you use Alice or Bob's frame of reference, you're going to use the same amount of gas on your trip, okay? And so what we can say here is that length or distance is conserved. If I could spell, that would help. Length is conserved when you rotate your coordinate system. So another way to say this is that we have an invariant quantity. Okay, and that is, in this case, that's the distance from home to work. Okay. Now, what we're going to see when we get deeper into special relativity is that length is no longer a conserved quantity when you change reference frames. We're going to see that the length of an object depends on the speed of that object in a given reference frame. Okay. However, what we're going to find is there are invariant quantities. There are quantities that all observers will agree on. It's just that in special relativity, that quantity does not just depend on distance. It depends on time intervals and length intervals. So we're going to introduce later an invariant quantity that all observers agree on, but that quantity will depend on x and time, t. So we just talked about coordinates. In that case, coordinates of objects in a two-dimensional space-only environment. Throughout relativity, we're going to make heavy use of this idea of an event. And an event is just something that happens at a specific instant in time at a single location in space. So some examples of events might be one photon emitted from a laser. Okay, that photon comes out of the laser at a single instant of time, and it happened at a single location in space. Another might be a photon arrives at a detector. Photon arrives at detector. Okay. How about the following? A photon travels across a room. Is that an event or not an event? Indeed, it's not an event, and it's not an event because traveling across a room implies much more than one instant of space and much more than one instant of time, right? This is a photon traveling across the room, spans the whole length of the room, and it takes some time for that to occur. Photon emitted on one side of a room is an event. Photon reaching the other side of the room is an event, but the whole journey is not a single event. Okay. How about, Physics 100 class on Wednesday? Is that an event or not an event? I would say not an event, right? Because first of all, the time of that class is about 75 minutes. So that's not an instant of time. And you could argue that the class takes place in an area that's the size of the classroom. Or, if we're remote, then it's kind of taking place across the planet. So we have a couple problems with that. Now, you could say the start of Physics 100 class for a particular person, right? And that person would have a given location, and the class would start at a single instant of time. So that would be okay. So think about events. Just take a minute and think of a few events that actually qualify as an event in the lingo of special relativity. Any event or example that you came up with would have to satisfy this idea that an event can be labeled by a single set of 4 numbers, time, and then the location of the event. So we're going to think about events as coordinates in a space and time continuum. And for us, we're only going to consider one-dimensional problems. So the event simplifies to a time and an x coordinate because we're not going to think about y and z coordinates. Everything we'll do this semester with relativity will be one-dimensional, so it should be more straightforward. But everything that we talk about as an event has to occur at a single time and at a single location on the x-axis. In another video, we're going to talk about drawing diagrams to represent activities. So we're going to draw snapshot diagrams that represent the situation that we're studying. And each of those diagrams is going to represent a single instant of time. So it's a snapshot in time showing objects at different x coordinates, different positions. So anytime you draw a diagram that represents one of these problems, that's a snapshot in time. And so if you want to draw 2 different events that are happening at different times, you need a different diagram for each of those events. So in closing, in this video, we talked about coordinates and how different coordinate systems imply that objects or points in that space will be labeled with different numbers, even though distances between those points are conserved, at least for regular geometry. What we're going to see in the future is that in relativity, distance and length between objects is not conserved. That will depend on reference frame, but there will be a conserved quantity that involves both space and time coordinates such that that quantity is conserved and is the same for all observers. And in order to talk about that in more detail, we introduced this idea of an event, which was a single, an occurrence that happened at a single location at a single time. So we'll talk much more about that going forward.